In section 8.3, we will learn about trigonometric integrals. These are integrals whose integrands involve all kinds of powers and products of trigonometric functions. Our skills for this section will be based entirely on the basic trigonometric integrals. So let's begin to develop that foundation by reviewing the integral formulas that we know and developing a few new ones. From Calculus 1, you learned that the integral of sine of x dx is negative cosine of x plus c. And of course, that's related to the derivative formula. We know that the derivative with respect to x of cosine of x is equal to negative sine of x. So the integral is simply the reversal of the derivative formula. Similarly, you learned that the integral of cosine of x dx is sine of x plus c. Relate that to its corresponding derivative formula. The derivative with respect to x of sine of x is cosine of x. As for the other four integral formulas, tangent, cotangent, secant, and cosecant, those integrands are not the derivative of any original function, or at least a familiar function. So we don't have a simple derivative formula that we can reverse to produce these integral formulas. So we're going to derive these integral formulas based on a new formula we've learned for Calculus 2. Namely, the integral of 1 over u du is equal to the natural log of the absolute value of u plus c. We're going to apply this formula to the following four trig functions, and we'll be able to generate their antiderivatives. Let's begin with the integral of tangent of x dx. Now, we're going to rewrite this function as sine of x over cosine of x. Then we can evaluate this with a u substitution. If we let u equal the denominator, cosine of x, then we can see that du is negative sine of x dx. That's what we have in the numerator of our integral. Of course, we need to solve for sine of x, so sine of x dx is negative du. So in terms of u, this integral becomes 1 over u times negative du. Or we could see that as negative integral of 1 over u du. And that's now an easily recognizable formula. We can integrate to obtain negative natural log of the absolute value of u plus c. Replacing u with its original function of x, we have negative natural log of the absolute value of cosine of x plus c. Thus, we can add to our bank of integral formulas here. The integral of tangent of x, then, is negative natural log of the absolute value of cosine of x plus c. So that's definitely a valid formula, but another way that you may see this formula presented is by applying log properties. If I take this -1 coefficient and I put it as the exponent on the argument, as logarithms allow me to do, then we would have natural log of cosine raised to the -1, or the reciprocal of cosine. The reciprocal of cosine is secant, so another possibility is natural log of the absolute value of secant of x plus c. Both of those are valid ways to integrate tangent of x. Now, you can imagine a similar process for integrating cotangent of x. Instead of sine of x over cosine of x, we have the reciprocal cosine of x over sine of x. We would make a u substitution for the denominator, and the result would involve a natural log. We would obtain natural log of the absolute value of sine of x plus c. Again, it has a very similar derivation. Let's also examine the integral of secant of x. So to determine the antiderivative of secant of x dx, we're going to do some clever algebra. I'm going to take this function, secant of x, and I'm going to multiply by secant of x plus tangent of x on the top and the bottom. So essentially, I'm multiplying that original integrand by 1. Now, why on earth would we want to do this? Well, if I look at the original integral of secant of x, that's the same thing as the integral of 1 over cosine of x. An ordinary u substitution, u equal to cosine of x, would not be sufficient because the derivative, sine of x, is also not present in the integrand. But notice when I apply this clever factor, what's going to happen? If we distribute secant into the numerator, we would end up with secant squared of x plus secant of x tangent of x. And then the denominator stays the same, secant of x plus tangent of x. Now, do recall that the derivative with respect to x of tangent of x is secant squared of x, and the derivative with respect to x of secant of x is secant of x tangent of x. Those are basic trigonometric derivatives. So what I see here in the numerator is a secant squared term. That's the derivative of tangent. And the second term is secant of x times tangent of x, which is the derivative of secant of x. So by introducing this interesting factor, which equivalently is 1, we can now make a u substitution. We will say, I'm going to work over here to the side, let u equal the denominator, secant of x plus tangent of x. Then du is going to be the derivative of secant, which is secant of x times tangent of x, plus the derivative of tangent of x, which is secant squared of x, all of that, of course, times dx. So the entire numerator then can be replaced with du, whereas this denominator is u. So rewriting this integral in terms of u, we have very simply integral of 1 over u du, which we know is the natural log of the absolute value of u plus c. When we go back to recover our original variable, we know that u was secant of x plus tangent of x. So by that clever algebraic trick, by introducing that interesting factor on the top and the bottom, we were able to obtain something that we could integrate with a u substitution. So we can add to our list of formulas the integral of secant of x dx is equal to the natural log of the absolute value of secant of x plus tangent of x plus our arbitrary constant of integration. Now we're not going to take the time to derive it, but the integral of cosecant of x dx is produced with a similar process. The result here, we would end up with the negative natural log of the absolute value of cosecant of x plus cotangent of x plus c. Now we do have a lot of information here, so let me highlight what is important. The foundation that we're building here is developing the integral formulas for all of our 6 basic trig functions. So the first one, the integral of sine, is negative cosine of x plus c. The second one, integral of cosine of x, is sine of x plus c. And of course, as we mentioned earlier, those integral formulas are dependent on our derivative formulas. Today, we added the integral of tangent of x. You've got 2 possibilities for that one, and either one is acceptable. And we have a related integral of cotangent of x, which looks something like this. Then the last 2 trig functions, secant and cosecant, they are derived similarly. We have a formula for the integral of secant and a formula for the integral of cosecant. So you definitely want to memorize those 6 basic integral formulas. It's important that you have them memorized so that you can recognize these patterns as they pop up in random problems. You don't want to have to go back to your formula sheet every single time you see the integral of a trig function. These formulas will also be necessary information to you have accessible in your brain as you go through Calculus 3 and differential equations. Now, as you're learning these integral formulas, it's also not a bad idea to take this opportunity to go back and review the derivatives of your 6 basic trig functions. We've got 4 of them listed on our notes at this point. So here's the first one, derivative of cosine, we have derivative of sine, we have derivative of tangent, and derivative of secant. So make sure that you know those. And just to make sure we have a complete list, there's 2 missing derivative formulas. Let's add them. The derivative of cotangent of x is negative cosecant squared of x, and the derivative of cosecant of x is negative cosecant of x cotangent of x. So on your notes here, you've got the derivatives of the 6 basic trigonometric functions, and now you also have the integrals of the 6 basic trigonometric functions. Now, while you're at it, learning new formulas and refreshing your memory on old formulas, this is also a good opportunity to review some important trigonometric identities that will be invaluable to us in this section. And those include the 3 basic Pythagorean identities. Now remember, if you know that first basic Pythagorean identity, sine squared of x plus cosine squared of x equals 1, then you can use that to generate the other 2 if you happen to forget the other 2 identities. For example, if I go through and I divide each of these terms of the original Pythagorean identity by sine squared of x, then I would end up with, reducing here, I would end up with 1 plus cosine over sine, that's going to give me cotangent of x squared, and then 1 over sine squared here would give me cosecant of x squared. So again, by dividing the original Pythagorean identity through by sine squared, you'll get the appropriate format for that last trig identity. And then with that strategy, you can probably figure out if I divide all 3 terms of the original Pythagorean identity by cosine squared of x and simplify, sine over cosine squared gives me tangent squared, cosine squared over cosine squared gives me 1, and 1 over cosine squared gives me secant squared. So I tell you that as a backup plan. If you're in a crunch and you don't have formulas, you're taking a test or something and you can't remember the trig identities, as long as you know that first one, you can generate the other 2. But it is really best if you know those Pythagorean identities like the back of your hand. You're also going to see in this section that it's important to know the half-angle identities. Now, the half-angle identities may not have been presented this way in your trig book. So let me show you just one little difference. One way that you may have seen this half-angle identity in your trig book would look something like this. So really, these 2 formulas are the same. Notice on the right side, this is maybe the way that you learned the half-angle identity. Sine of x is isolated. So if I square both sides of this equation, I'm going to be able to eliminate the radical and also that plus or minus sign. So I'll be able to express this with one equation. That is, I don't have to have that plus or minus there. Also, notice the relationship between the angles. The angle that I have in the argument on this side is exactly half of the angle that I have over here. And that's the relationship that we see on the identity that's listed. This angle is exactly half of this angle. So the format that's going to be most useful to us for our integrals will be the ones or the presentation that we have here. But if it helps to relate it back to how you learned it in trig and look at a new variation, then all the better. And again, just for comparison, you may have learned this second half-angle identity in a format that looks something like this. So if you take the version that you learned from trig, square both sides, and then recognize the relationship between the angles, that is, this angle is exactly half of this angle, then that association will help you to learn it a little bit better. But once again, let me emphasize, the way that we will be applying these half-angle identities is in the format that you see listed here on your notes. Now, if you're totally rusty and you can't remember the half-angle identities from trig, no big deal. You can go ahead and memorize them in this format. Now, let me also point out a pattern. Earlier in the semester, we talked about hyperbolic trigonometry, and I pointed out a sine pattern, and that same pattern appears here. Remember, we were talking about hyperbolic sine and how it goes with the negative version of the exponential definition? Well, we can see that here as well. Sine is associated with the negative one, cosine is associated with the positive version. Notice both of these are given in terms of cosine. Sine squared is identified in terms of cosine of 2x, cosine squared is identified in terms of cosine of 2x. So the same relationship you saw with hyperbolic sine, hyperbolic cosine, and the positive and negative patterns, that's the same pattern that we're seeing here. We have ordinary sine squared, ordinary cosine squared, but we see that sine goes with the negative version of the formula, cosine goes with the positive version. The way I remember that, sine looks like sin, and sin is bad or negative, right? So if that helps you to remember those formulas, then that's awesome. So there are a lot of fundamental formulas that we're looking at here. Again, this will build the foundation for more complicated integrals. So it's really important that you have a working knowledge of these formulas. So please take some time to memorize those.